Okay, going to be working 13.2. This is line integrals. And I guess I'll start with number 1. For the line integral of the scalar function y cubed with respect to s, which is arc length, over the curve C, where C is given to us by the parametric equations x equals t cubed, y equals t, and t is bounded between 0 and 2. All right, so all we need to do here is come up with, since we already know the function, the scalar function here, y cubed, we will simply replace that with t, so it'll become t cubed. But ds, remember, is equal to the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. So we're going to need to compute this. Let's go ahead and do it right here. This is square root of derivative of x with respect to t is going to be 3t squared, and the derivative of y with respect to t will just be 1. And so we're going to have 3t squared squared, which will give us 9t to the 4th, plus the derivative of y with respect to t, which is 1 squared, which is 1. And, oh, I'm sorry, I forgot. Out here, we'll have dt. So this will become the integral from, and now over this curve, t is going to be our variable, so t varies from 0 to 2. Y cubed, again, I said that would be this cube, so t cubed. Then ds, which is the square root of 9t to the 4th plus 1 dt. And we just need to evaluate this integral now. And we notice that we can do this with just a basic u substitution. If I let u be equal to 9t to the 4th plus 1, the derivative is going to be 36t cubed dt. I have a t cubed dt, so I'm going to divide both sides by 36, so 1/36 du is equal to t cubed dt. And so this will be replaced with t cubed dt will be replaced with 1/36 du. I'll just show you what the new integral is right here. 1/36 du, and then I have the square root of u, so I'll say u to the 1/2 like that. Now take the antiderivative of this, so add 1 to this, you get 3/2, so 36 times, you have to scale in front, so 1/3/2, same as 2/3, u to the 3/2. And then I can clean this up a little bit. Let's see, 2 goes in here. What is that, 18 times? And 18 times 3 is 30, 40, 54. So we should have 1/54 u to the 3/2, but u was 9t to the 4th to the 3/2. Okay, now we go in and I'm going to come back over here and say, all right, this is equal to 1/54 9t to the 4th plus 1 to the 3/2 evaluated, let's see, 0 and 2 here. And plugging in 2, we get what? 2 to the 4th power is 16 times 9. So 1/54. Let's see, 16 times 9. That's 90 plus 54, that's 144. So we have 144 plus 1 to the 3/2. That's what we get when we plug in 2. And then when we plug in 0, we get 1 over 54. Let's see, 0 here kills this off, plus 1, so that's just 1. 1 to any power is 1, so we just get 154 times 1. And so we have 154th. I'll go ahead and factor out a 154th from both of those. This is 145 to the 3 halves minus 1. That's our exact answer. Don't see that we're going to be able to simplify that at all. Yeah, we can just leave it like that. That's good. So that's it. That's the value of the line integral. Let's see, let's look at number 3. For 3, we have line integral over the curve C. Here's our scalar function, x, y to the 4th, with respect to, again, arc length. And C is the right half of the circle, x squared plus y squared equals 16. So if I graph this, it's the right half of this circle. So we're talking about here, radius of 4 because we've got 16 there. So that's our curve C. And so what I need to do is come up with a parametric equation for C. So C, well, I know how to draw a circle. I can let x be equal to here 4 cosine t. That'll give me a radius of 4. Y will be equal to 4 sine t. And now I need some bounds on t. Well, I want to draw this circle only the right half. So I'm going to try and draw it like this. So what I'll do is I'll start at negative pi over 2 and go to pi over 2. So let's just double check. If I plug in negative pi over 2, cosine of negative pi over 2 is going to be 0 times 4 is 0. So basically when I plug in pi over 2, negative pi over 2 for t, what I get out is x will be 0. And then y, let's see, sine of negative pi over 2. So sine of negative pi over 2 is negative 1 times 4. That gives me negative 4. So I will be at 0, negative 4. So I will start here. And then as I start moving through, I know at pi over 2, this will turn to a positive. So I know I'm going to end up here. And we could just kind of trust that it's going to draw it this way. But let me just check one more point. What about t of 0? We should be here. Let's see. T is 0, cosine of 0 is 1. 1 times 4 is 4, so we get x is 4. And sine of 0 is 0, so we just get 0 there. So yes, we are here. So that should do it for us. So now I'll just come back and think about what I need for this. I need ds. So ds will be equal to the square root of the derivative of x, which is with respect to t, derivative of this squared. So derivative of that, let me just write down underneath here the derivative. I'll just write x prime. This will be negative 4 sine t, and the derivative of y will be 4 cosine t. So if I take the derivative of x and square it, I get 16 sine squared t, plus now the derivative of y, which is this squared, which is 16 cosine squared t dt. And I can factor 16 out of this, and then I'll get sine squared t plus cosine squared t is 1, and then I'll have square root of 16. But the square root of 16 is 4. So ds should be equal to 4 dt. That's nice. So let's go back up now, and let's rewrite this. This will be the integral from negative pi over 2 to pi over 2. X, which is 4 cosine t, okay, times y to the 4th, which is this to the 4th. So 4 sine t to the 4th. And then ds, which is 4 dt. All right, so this will be, see how many 4s do I have? 4, 4, it's 4 squared, and then I have 4 to the 4th. That's 4 to the 6th. I'm going to factor that out as a constant. And then I'm going to write it this way, sine to the 4th t cosine t dt. And I'm kind of hot. Give me a second here. It's hot in this room. Okay, so at this point, I noticed that if I just let u be equal to sine t, the derivative of that is cosine t dt, which I have right here. So this is just a direct, clean, easy substitution. I'm going to get, let's see, this equals 4 to the 6th. So I'm taking the antiderivative of this. It's going to be this. This is like the u. So I have u to the 4th. The antiderivative of that is going to be 1/5 u to the 5th, but that's sine to the 5th t. And I'm evaluating this from negative pi over 2 to pi over 2. All right, so now let's plug in some values. So let's plug in pi over 2 first. So I get 4 to the 6th times 1/5 times, now sine of pi over 2 is 1, to the 5th power is still 1, so we just get that, times 1, minus, then when we plug in negative pi over 2, sine of negative pi over 2 is negative 1, but then to the 5th is still negative 1, so this is just going to turn into negative 4 to the 6th times 1/5. And I get a negative and negative, which is positive. So I'm basically adding that to itself, so I get 2 of them, right? Let me write it this way. I have 4 to the 6th over 5 plus 4 to the 6th over 5. They have the same denominator. So that's going to be 2 of the 4 to the 6th over 5. And let's see if I want to get the actual answer here. Yeah. No, they don't expand that out. They get it as a decimal, 1638.4. Approximately 1638.4. Like that. All right. That's it for number 3. Let's see what number 5 looks like, if it's worth doing. 5. Yeah, I'll do 5. Why not? So for 5, we have line integral over c. Here's our scalar function, x squared y cubed minus root x. Oh, dy. Okay, that's a little different. Then c is the curve. Y equals root x. And from the point 1, 1 to the point 4, 2. Now, it's kind of important that they tell us it's going from this point to this point, because we saw in class that when you do line integrals, the direction of the path, or the direction you travel along C matters. Now, when you're doing a line integral with respect to arc length, it doesn't matter which direction, you get the same answer. But when you do it with respect to y or with respect to x, your answer will differ by sign depending on which way you go on the path. So we want to make sure we understand where we're headed here. So let me draw this real quick. This is what square root of x looks like right here. It's y's root x. But we only want to go from 1, 1, so from this point to the point 4, 2. So we're only traveling along that piece right there, C. So to do this, we need to find parametric equations for this. Because y is a function of x, what we always do whenever y is a function of x, we just let x be the t. So the independent variable becomes t, and then the y will just be the function, square root of x, but remember x is t, so it's just root t. And now t is going to be constrained here. Well, t is our x value, so our x values are stuck between 1 and 4 here, so 1 to 4. I also need, in this particular problem, I need dy. So dy is just the derivative of this. And the derivative of that is 1 over 2 root t. And remember that the dy actually comes from the formula for ds, where you go dx dt squared plus dy dt squared, and we're saying that that's 0. And so you get dy dt squared square root. So that's why it's just dy. So we don't have to square it. All right, let's do this. We've got the line integral. We're going to go from 1 to 4. And x squared, which is this squared, so t squared, times y cubed. Now remember, this is y. I can write that as t to the half. Right, so I'm going to cube it, so it's going to become t to the 3/2 minus the square root of x, which is this square root of t, and then dy, which we said right here is 1 over 2 root t dt. I should have written over here. Well, this is fine, but really what that is dy dt equals 1 over 2 root t, and you just bring the dt to the other side. Okay, now that I see this, I think what I'll do is I'm going to rewrite this. This right here, t to the 3/2 is the same as, how can I write this? Yeah, this is t to the half cubed. That's what I did. That was square root of t cubed, which is square root of t times root t times root t, and those two together are t. So I'm going to rewrite this as root t times t. The reason I'm doing that is because I'm going to distribute this through here, and the root t's are going to cancel. So let's distribute here and here. We'll get integral, we can go 1 to 4. When I do this to this, this root t and that root t cancel. So all I'm left with is a t cubed over 2. So I'll write 1/2 t cubed. And then when I go here to here, the roots cancel. I just get minus 1/2 dt. And this, I can pull a 1/2 out of everything and be left with t cubed minus 1 dt. And this is 1/2, all right, times antiderivative here, 1/4 t to the 4th. Antiderivative here is t, 1 to 4, and then plug in. So let's see here, here's number 5. Let me just tell you what the answer is, 243 over 8. So I'm not going to go through that work. All right, let's look at number 7. Maybe we'll look at number 7. I guess I'll do 7. So for 7, I have line integral over c of x plus 2y dx plus x squared dy, where c consists of the line segments that go from 0, 0 to to 2, 1. And then from 2, 1 back to 3, 0. So I'm going to say this is C1 and this is C2. I'm going to have to break this up into 2 different pieces. Yeah, so let's define these 2 curves, curves. Remember, this is 0, 0, this is 2, 1, and this is the point 3, 0. So if I'm going to define C1, it's going to be a line segment. So I'm going to define it to be with this vector function we call R1 of t. And it's going to connect this point to this point. So I'm going to start at 0, 0. And then t, and then the direction vector that goes from here to here, which is just 2, 1. We did this in class, so I'm assuming you're okay with that. Making sure that it shows up on camera. Yeah. All right, and then that's just R1 of t is, add those together, you should just get 2t and then t. So if you want to convert this to parametric, I have an x and a y. I'll call it x1, y1 so we don't confuse it with the C2. This is 2t and this is t. Now, to get C2, I'm going to call R2 of t. We're going to start at 2, 1, and we're going to go to, that's t, this point. So the vector going from here to here is going to be the vector 1, negative 1. And then we put those 2 together. This is going to be 2 plus t, and then 1 minus t. So the x and the y are going to be 2 plus t and 1 minus t. All right, so those are the parametric equations for the 2 curves. And what I need to do here is realize that this is actually going to need to be written as 2 different integrals. This is going to be integral over C1 of x plus 2y dx, and then this part over C1. So I'm going to say plus over C1 x squared dy. So that's just rewriting the notation. This really means 2 integrals. Then I'm going to say plus, now I'm going to go over C2 of that, x plus 2y dx plus over C2 of this one, which is x squared dy. All right. So remember, this notation means integral, integral. But then, so that's this. But then I need to go over, C is actually 2 curves, so this is the first curve, and then add the next one. All right, now converting. So I'm going to go over C1 right now. And because I'm going to integrate over C1, I'm going to use these 2 right there. So this will become, oh, you know what? I forgot to put the restrictions on t. On both of these, t is between 0 and 1. And that's just because of the way that we have learned how to draw line segments. T will always vary between 0 and 1. All right, so this integral will go from 0 to 1. It'll be the x, which is 2t, plus 2 times y, but y is t, so 2t again. And then dx, which is the derivative of the x, which is just 2 dt. All right, then we have plus, next integral, still going over C1, so 0 to 1, x squared, which is this squared, which is 4t squared, times, this time derivative of y, which is derivative of t, which is just 1 dt. Plus, now we're going to go over, I wish I had another color, but I don't. We're going to go over C2, so we're going to be looking at these 2 now. So we've got plus, this one right here goes from 0 to 1 also. X, which is, in this case, 2 plus t. Plus 2 times y, which is 2 times this, which is going to be 2 minus 2t. And then times dx, which is derivative of this with respect to t, which is just 1 dt. And I have one more integral to squeeze in here. Plus integral from 0 to 1 x squared, which is going to be this squared. So 2 plus t squared. And then dy, so the derivative of y is, look, negative 1. Be careful here. So this is going to be negative 1 dt. All right. Now, notice all of the integrals go from 0 to 1. So I'm going to turn this all into one big integral, and they're all with respect to t. Let me clean them up first. This right here, if I put that together, pass the 2 through, I get, well, okay, let's do it this way. This right here is 4t, then times 2 is 8t. So I've got 8t here. Here I've got 4t squared, so plus 4t squared. Here, let's see what I've got here. 2 plus 2, that's 4. T minus 2t, it's minus t. So 4 minus t, so plus 4 minus t. And then here, when I square that, I get 4 plus 4t plus t squared. But then I make it all negative. So minus 4 minus 4t minus t squared. That's all my t's now in one big integral dt. And I should be able to clean that up. Let's see, let's count my t squareds first. How many t squareds do I have? I've got 4t squared, take away 1t squared, that leaves me with 3t squared. How many t's do I have? 8 t's. Take away a t at 7 t's. Take away 4 more, we get 3t. And then 4, take away 4 is gone. So that's it. So this is going to be t cubed plus 3 halves t squared. 0 to 1. So plug in 0, it's all gone. So I just have to plug in 1 here. 1 plus 3 halves, which is 5 halves. See if that looks right. Yeah. Okay. Good to go. Good to go. Okay, let's look at number 9. See how I'm doing on time. I've got time. XYZ ds, where C is given with the parametric equations. X is 2 sine t, y is t, z is negative 2 cosine t, and t is between 0 and pi. All right, so for this problem, notice this is the first one that we've done so far, where our scalar function in here is a function of 3 variables instead of 2. Our parametric curve has 3 equations. Our curve has 3 parametric equations, so this is a 3-dimensional curve, and it's given to us, which is nice. We don't have to generate the curve ourselves. So let's do this. Let's figure out what we need. We know what x is, we know what y is, we know what z is. We can convert all those over. ds is really the big piece right here. So we're going to need to do ds, which is going to be the square root, and I'm going to write it this way. It's the derivative of x squared plus the derivative of y squared plus the derivative of z squared. So dx dt squared, dy dt squared, dz dt squared. So I'm going to need these derivatives, so I'll get them right here. My derivatives here, x dt, sorry, out here at the end. X prime is going to be 2 cosine t, y prime is 1, and z prime is positive 2 sine t, sine t. So when I take these and square them, for me, my ds is going to be here, square root of x prime, this squared, so 4 cosine squared t, y prime squared, which is just plus 1, plus 2 sine t squared, which is 4 sine squared t, dt. And then I see that I can put this one and this one together, factor a 4 out. Cosine squared t plus sine squared t will be 1, so I'm going to have a 4 plus a 1, that's 5, so this is just root 5. So all this ds is just root 5 dt. Let's see what this is all about. Give me just a second here. So this integral is going to turn into 0 to pi, x, which is 2 sine t, times y, which is t, times z, which is negative 2 cosine t, times ds, which is root 5 dt. And, oh, I see something. I see something. All right, integral 0 to pi. How about we do this? I wonder if I should pull the negative 2s, the negative 2 and the 2 out, make it a negative 4 or not. Pull the root 5 out. Let's just do it. Let's just pull all the constants out. Negative 4 root 5. And what we're left with is sine t, cosine t, and then a t in front of all that, like that. Which, this is why I was curious if we should pull that out. This is almost a double angle formula. So let's try something here. Let me rewrite. So I'm going to push a 2 back in. Negative 2 root 5, integral 0 to pi. I've got t times 2 sine t cosine t dt. And now this is sine 2t. And so I have negative 2 root 5 integral 0 to pi of t sine 2t dt. And to integrate that, I think we're going to probably need integration by parts. Let's see how this goes. Let me make a table here. U is t. dv will be sine 2t dt, and then the derivative of u with respect to t is going to be just 1 dt, so just dt, and the antiderivative of this will be negative 1/2 cosine 2t. So check it for yourself. The derivative of this is this. So I can do integration by parts, and so this right here will become negative 1/2 t cosine 2t. So I'm doing, the formula is u times v, so those two, minus the integral of v du. And I notice I have a negative 1/2, which I'm going to pop out here, and that'll come out and make that a positive 1/2. integral, and then all I'm left with is the cosine 2t, like that, dt. And that's negative 1/2 t cosine 2t. The antiderivative of this actually is 1/2 sine 2t, and I already had the 1/2 here, so I think we're just going to have 1/2. Well, let's see here. 1/4 sine 2t. So check that. If I take derivative of sine of 2t, I get cosine of 2t times derivative of what's inside, which is 2. That hits that, I get the 1/2. So I'm good. I'm good. All right. That's the antiderivative. Now I still have this in front of it, and I have to evaluate it. So we have that this is equal to negative 2 root 5, it's this, times this, which is negative 1/2. So this negative 2, and that negative cancels. So really, I could just say that that's all just root 5. How about that? Root 5. Okay, t. No, it's all that. Let me be safe here. Hold on. Negative 2 root 5 times all of this. Negative 1/2 t cosine 2t plus 1/4 sine 2t evaluated from 0 to pi. And now I could pull out a negative 1/2, but I'll just leave it. Let's plug in pi. Negative 2 root 5 times, if I plug in pi here, cosine of 2 pi is 1, right? So this turns into a 1, but then times t, which is pi. So I get negative 1/2 pi. Sine of 2 pi is 0, so all that's gone. So that's all I have when I plug in pi, minus negative 2 root 5. Then cosine of 0, right? Cosine of 0 is 1, but then times 0, it's gone. And then sine of 0 is 0. So this is all 0. It's all gone. This whole thing is gone. And so we should just get, let's see, negative and negative is positive. The halves cancel. Get root 5 times pi. Interesting. Nice. I'm going to let you try and handle 11 and 13. I think on 11 it's pretty straightforward. You're gonna have a basic U sub on that. On 13, it's also a basic U sub, so those work out pretty nice. All right, let's go and do number 19 now. For 19, we're asked to evaluate the line integral, but this time we've got a vector field, f dot dr, all right, where f is given to us as a function of two variables, so it's two-dimensional vector field, and it's x, y, I hat plus 3y squared j hat, and they give us that r of t is 11 t to the 4th I hat plus t cubed j hat, and they tell us t is between 0 and 1. Okay. Let me get some stuff in order here first. I'm going to rewrite f the way I did in class. F is going to be, I'm going to write it as a vector. So it's I and j, those are your components. So x, y 3y squared. R of t is, again, two components, 11t to the fourth t cubed. And then, of course, t is between 0 and 1. So what is f, the vector field f dot dr? Well, we saw in class that there was a couple of formulas for this, but we're going to use the one where we have probably this one. It's going to be the integral from a to b of f dotted with the derivative of the r function dt, like that. So I need to dot these two together, but I actually need to, hold on, I left out something. It's f with the vector function, the curve plugged in, dotted with the derivative of the curve dt. So we know the limits of integration here because we're going with respect to t. That's going to be 0 to 1. All right, we need to take the f and we need to plug in our curve. So that means take this vector field, f, plug in the curve to it, which means we're going to get a vector. I take the x times the y. So I look to my curve. Here's the x, here's the y. I'm going to multiply the two together. So that gives me 11t to the 7th. Then this next component is going to be 3 times y squared. So I'm going to take 3 and then square the y. Squaring that, I get t to the 6th. That's the first part of this. Dot that with the derivative of r. So the derivative of r, I'll write it down right here. It's component by component differentiation. So 44t cubed 3t squared. So 44t cubed 3t squared dt. So I just need to dot those two together. Dot products are pretty clean. $440, $484. I believe we get 484 there. So I'm going to multiply these two together. And remember, with dot products, you're just adding. You add after you multiply the components. You add these things together. So 484 t to the 7th times t cubed is t to the 10th plus 3 is 9 t to the 8th dt. The answer should come out to be 45. I won't do the rest of that. All right, next one. Got about 10 more minutes. Let me do I think the rest of these are pretty clean. I'm not seeing anything crazy. I think you can probably do the rest of those. So they give you everything you need. Okay, I'll do one more. Jeez. I'm not going to be able to get to the word problems, I don't think. Not yet. So they give us a vector field. This time the field has 3 components. It's x, y, and x times y. So x, y, and xy. And then they give us our curve. R of t is cosine t, sine t, t. And they give us that t is between 0 and pi. So I know I'm going to need the derivative. Negative sine t, cosine t, 1. I also know I need to take the vector field and plug the curve into it. So when I plug the curve into it, that means I'm going to replace x with this, y, and then z. So x, that's going to be just cosine t. The y is just going to be sine t. And the z component is going to be x times y, so this times this. So notice that we didn't even use that t. Cosine t, sine t. All right. So I'm ready to set up the integral. The integral over c of f dot dr is equal to the integral from 0 to pi of the dot product of this right here, cosine t, sine t, cosine t times sine t, dot that with the derivative right here. So negative sine t, cosine t, and 1 dt. And when you multiply cosine times negative sine t, you get integral 0 to pi. Cosine times this is going to be negative sine t cosine t. This times this, you get positive sine t times cosine t, so those are going to be gone. And then this times this, which gives you another one of those. Sine t cosine t dt, gone, gone. You're integrating sine t cosine t dt, which is 1/2 sine squared t, evaluated from 0 to pi. And if you do that evaluation, what number was this, 22? You should get 0. And I still have a little time. All right, next one on 37. I don't know. I mean, I think 37 is pretty straightforward. I think 39, I mean, it's basically just like the problems I just did. They give you f, they give you the r. On 39, the only thing I'll say, let me do 39. I won't do 37, I'll do 39. Or at least I'll set it up. So they give you this field in vector form. It's, let's see, x minus y squared. It's y minus z squared. And z minus x squared. And the path, the particle is moving along a straight line segment that goes from the point 0, 0, 1 to the point 2, 1, 0. So I'm going to come up with a vector curve that'll do this for me. R of t will be equal to, I'm going to start here, so 0, 0, 1 plus t times, and now the vector going from here to here will be 2, 1, negative 1. And if I put those together, I get, let's see, 2t, t, and 1 minus t. So this is your x, your y, your z. I think that's all I need. Oh, and then t varies between, of course, 0 and 1, because I'm drawing a line segment. All right, so I should be able to set this thing up. I'm going to squeeze it in right here. Integral over c, vector field, f dot dr should be equal to the integral from 0 to 1 of f with r plugged in. So here's r. I'm going to plug in for x, y, and z into that. So x, which is 2t minus y squared. This is y squared, so t squared, comma. Y, which we know is t, minus z squared, this time is this squared, so 1 minus t squared. And then z, which we know is 1 minus t minus x squared, but x is 2t squared, you get 4t squared. So that right there represents our vector field along that curve, right? With the curve plugged in. I want to dot that with the derivative of the curve, r prime. So derivative of 2t is 2, the derivative of t is 1, and the derivative of 1 minus t is negative 1. That's a pretty nice dot product to do. So this is going to be integral from 0 to 1. I take this, I multiply it by 2, so I get 4t minus 2t squared. I take this, I multiply it by 1, which is just plus t minus 1 minus t squared. I take this, I multiply it by negative 1, which changes it to minus 1 plus t plus 4t squared dt. And I can clean that up a little bit more. So integral 0 to 1. Let's see, this right here is 1 minus 2t plus t squared, but then there's a negative in front, so minus 1 plus 2t minus t squared. So just remember, that's replacing all of that, okay? So let's look at t squareds. I have negative 2t squared minus t squared, it's negative 3t squared plus 4t squared. So should just get t squared. And then t's, I have 4t plus t is 5t, 6t, 7t, 8t. So my t's are done. And I forgot this t. There we go. And then as far as numbers are concerned, minus 1 is minus 2 dt. What number was this? 39? The answer to that is 7/3. There we go. All right, I'm gonna wait to do the rest on the next video, but that should be enough to get you going. All right, I'm still working here in 13.2. Decided to go ahead and do some of these later problems. Here's number 40. I'm going to read the problem out here. The force exerted by an electric charge at the origin on a charged particle at the point x, y, z with position vector r is equal to the vector x, y, z is given to us by the force, the field, as a function of r is equal to k times r over the magnitude of r cubed, where k is a constant. Find the work done as the particle moves along a straight line from 2, 0, 0 to the point 2, 1, 5. So we want the work done, so we definitely want to compute the line integral over C of f evaluated at r of t dot dr. Now, we need to come up with the parametric representation for this line segment. And to do that, we've done this before, I'm going to look at r of t to be equal to, let's see, the starting vector 2, 0, 0, plus t times the vector that goes from here to here, so 0, 1, 5. And so this equals, let's see, 2, and then we get t, and then 5t. There we go. So there's the parametric representation for the line segment. And now what we want to do is we want to plug this into our vector field. So we're going to put it here and here. We'll have to take the magnitude of it and then cube it. But then we're going to dot it with dr. And dr is, let's see, we take dr, here's the derivative of r of t, which is just going to be 0, 1, 5. We're going to be dotting that, so that's that, dotting it with this dt. So let's go ahead and try and figure out what this is. So I'm going to do f of r of t will be equal to k times the vector r, which is 2t, 5t, over the magnitude of this, which is 4 plus t squared plus 25t squared. So that's the magnitude of it, but then cubed. But I'm going to dot that with this right here. So 0, 1, 5 dt. All right, so that is what we get. I shouldn't say that. This is f of r of t dotted with dr. So that's what we want here. We're going to set this up in an integral. T, of course, goes from 0 to 1. And that should be it right there. So let's see if there's anything we can do to help clean this up. Remember that k over all this is a constant. So we get integral from 0 to 1. Let me just dot these two vectors. This times 0 times 2 gives me 0. 1 times that gives me t. So I'm just looking at the dot product right now. Right now I'm going to get 0 plus 1 times t is t plus 5 times 5t is 25t. That's our dot product. And all of this, k over all this right here, square root of, I'm going to say 4 plus, I'm going to add those two together, 26t squared, all of that cubed dt. All right, so I hope you kept track of what I did there. This right here is a constant, right? So I dot two vectors and get a number or a scalar function. So this and this gave me this part, and then I just multiply it by this thing, which is going to be some constant. All right, let me clean it up. Integral 0 to 1. K, I think I'll pull the k out. This is going to be 26t on top. And then underneath this, I've got, I'm going to say 4 plus 26t squared, all of that to the 3/2 dt. And I'm going to make a basic u substitution here. I'm going to let u be equal to the entire expression in here, 4 plus 26t squared. The derivative of that will be 52 t dt. And you can see here I have 26 t dt. up here. So I'm going to divide both sides by 2. So 1/2 du is equal to 26t dt. And so I can replace this part with 1/2 du, and I can replace this with u to the 3/2. So I'll get something like this. This is just the integral, okay? Just the integral without the 0 to 1, okay? So this k, I'll get a 1/2, like I said, a 1/2 du, so I'll put 1/2 du, and then 1 over u to the 3/2, which is really u to the negative 3/2, and then I do my antiderivative. So 1/2 k, add 1 to this, we get negative 1/2, flip it, so negative 2 u to the negative 1/2, and plus some constant. So this is really just negative k over the square root of u, which was 4 plus 26t squared. So that's the antiderivative. So this is going to become equal to negative k over 4 square root of 4 plus 26t squared, evaluated 0 and 1. So when I plug in 1, I get, let's see, negative k over square root of 30 minus, and then when I plug in 0, I get negative k over square root of 4. So this is going to become, what can I do here? Negative k over root 30 plus k over 2. Let's see if we want to clean that up at all. I think that's the way the book leaves it. They factor out a k, but this is good enough. One of the confusing parts of this problem is the fact that when they give you R, they say, okay, R is x, y, z, and that's somewhat confusing when you look at it. What they're saying is that your R vector, okay, is, if you imagine three-dimensional space, you're moving along some line segment, right, which, wherever it was, we're moving along some line segment, okay, and we had to find the parametrization of that line segment, but they're just telling you that the R is actually the position of where you are in three-dimensional space. It is the x, y, and z components of that line segment, which we got. So I think that's one of the more confusing parts of the problem is why do they write that? Just understand that all they want you to do is get the parameterization of this and use the fact that the x will be x, y will be y, and the z will be z in each of those parametric equations. All right, let's look at, let's see, 42 is somewhat interesting. So for 42, we have an object with mass m. Okay, so you have an object that has a mass of m, moves with the position function r of t equals a sine t I hat, so I'm going to put that like that, plus b cosine t j hat, and then c t k hat, which is that, and it's on the interval 0 t, 0 is less than or equal to t is less than or equal to pi over 2. And they're asking you to find the work done on the object during this period of time. Well, problem here is that it's not just obvious that what the field is. All right, so we need, in order to compute the work, right, we need to know the line integral over c of the vector field evaluated on the curve, right, dot dr. Well, we know what r is, okay, so that's not a problem. We'll need its derivative, so may as well get its derivative here. That's going to be a cosine t, negative b sine t, and c. So a, b, and c there were constants. But what about the field? Well, what we can assume is that the field here we're talking about is a force because they're looking for work. So the vector field is going to be a force. Force, okay, the force vector is equal to mass times the acceleration vector. And we know from our study of vector curves that the first derivative represented the velocity curve, and then the second derivative would be the acceleration function. So what I need to do is take the derivative again, right, which would be the second derivative of our position. So take derivative of this with respect to t, we get negative a sine t, and we get here negative b cosine t, and then 0. So now if I'm trying to find my force, right, my force vector will be the mass times the acceleration, which we just found to be negative a sine t, negative b cosine t, and 0. And if I go ahead and multiply the m through as a scalar multiplication, just distributes, I get finally that my force vector, okay, is going to be equal to mass times this, so negative a times mass times sine t, and then mass times this, you get negative b times mass times cosine t, and then mass times 0 is still 0. So you just get 0 here. So there's my field, all right? And I don't need to plug in r of t into it, right? I don't need to plug r of t into it because this entire thing, right? This entire thing, you can see up here, is a function of t now. And the way we got it was using the fact that the field would be mass times acceleration. So I don't need to plug in, and it wouldn't make a whole lot of sense to plug in this into this, right? Like, how are you going to plug this in here? But you can kind of see it already. I mean, it's there. It's this is like the a sine t, and the b cosine t is there, and then the constant. Well, the fact that the acceleration was 0 wipes it out. So that's it. We just need to take that and dot it with r prime, which is this one. So this work will be equal to integral from 0 to pi over 2, because that was my restriction on t. This right here, which was negative a m sine t, and then negative b m cosine t, and then 0. And then I'm dotting that with the dr, which is this. So I'm going to run out of room. I think what I'll do is I'll rewrite this up here. So my work is going to be this from 0 to pi over 2, right, dotted with dr, which is this one, a cosine t, negative b sine t, and c dt. And then go ahead and do the dot. So let's do this. This will be equal to the integral from 0 to pi over 2. Okay, this times this, we're going to get negative a squared m sine t cosine t plus, now this times this, negative and negative is positive, so plus is fine, b squared m sine t cosine t, and then plus this times this is 0, so nothing, and then dt. So now We have some choices here. Let's pull out the sine t, cosine t from both of these. So if I do that, I get integral 0 to pi over 2. Okay, if I pull out sine t, cosine t from both of those, I'll be left with a negative a squared m, and I'll be left with a plus b squared. So I'm going to write that backwards. B squared minus b squared m, sorry, minus a squared m, and then sine t, cosine t dt. So since I'm integrating with respect to t, I don't even need to worry about that. The antiderivative of this is going to be, let's see, b squared m minus a squared m, and then times 1/2 sine squared t. So I just did a quick little u sub. This is u, that's du, so this is it. Evaluated from 0 to pi over 2. Then we plug in. Sine of pi over 2 is 1. 1 squared is 1. And then times 1/2, and then times that. So I just get 1/2. You know what? I'll factor an m out also. 1/2 m b squared minus a squared. And then when I plug in 0, sine of 0, 0 kills everything off. So you just get this. So that should be the work done. Which one was that one? 42. So I guess what I can stress to you again here is work, you know, was the line integral c of f dot dr. I mean, that's what it is, right? Now, if we come up with the parametric representation for the curve c, then we have to plug that into the vector field, right, in order to figure out what this f is. But for us, we didn't have to do that. To get f, we used the formula of mass times acceleration. So really, we're replacing this with this. It wasn't necessarily us trying to plug the curve into the field, right? We knew what force was, so we didn't have to think about it this way. All right, and then let me see, 43 is very much like one I did in class. So that was a man carrying a bucket of paint up a silo, okay? So, you know what, I'll look at number 43, and then I'll look at 44. So 43, you have a 160-pound man. He's carrying a 25-pound bucket of paint up a silo, up a helical staircase with the radius of 20 feet. So you have this silo. It has a radius of 20 feet, and it is 90 feet high. So what we did is we tried to come up with a way to parameterize that curve. Okay, you start off here, and it goes around 1, 2, I believe it said 3 or something like that. 3 times? Yeah, 3 complete revolutions. All right, so yeah, I think this is almost exactly like we did in class. So what is the force? First of all, the only force we have at play here is gravity, and it's acting, you can look at it 2 ways. You have gravity going down, which we could say is a negative force, or you could say the force of the man going up, countering the gravity. So we can look at the forces being either straight down or straight up. It won't matter. I'm going to look at it as being straight up. So a vector that goes straight up is going to have 0 for the x and y components, and then the force up would be 185. Okay, like that. Remember, pounds is a measurement of force, right? Pounds is a measurement of your mass times the acceleration of gravity. In other words, weight is a force. And now I need to come up with parametric representation of this curve. So the way we did is first we drew a circle with radius r, okay? So that was 20 cosine t, 20 sine t. but then we need to go up. And we need to go, well, I should say it this way. T right now has to be between 0 and 6 pi, because I want to do 3 full revolutions. So this will draw me a circle when t is between 0 and 2 pi. So I need to go around 3 times, so I need to go from 0 to 6 pi. So that draws me 3 revolutions, and in that time, when t varies from 0 to 6 pi, I need to only go up 90 feet. So if I write 90 over 6 pi t, that will be my z component, right, at t equals 0, right? T equals 0 here will be on the ground. And when I finally get to 6 pi cancel 6 pi, you'll be at 90. And it's linear, so you're going to go from 0 all the way to 90 linearly, which is the same thing that would happen if you look at someone going up the stairs. The z component is linear. All right, and then we did derivative here because we need dr, so negative 20 sine t, 20 cosine t, and this is just 90 over 6 pi. And so we're going to take our force and we're going to dot it with this, and then we're going to go ahead and get our integral of that. So when you dot these two together, what's nice is 0 kills this, 0 kills this. All you get is 185 times this. So all we're going to do is do the integral from 0 to 6 pi of 185 times 90 over 6, 90 over 6 pi, and then dt, and the antiderivative of that is 185 times 90 over 6 pi t, evaluated from 0 to 6 pi. And when you plug in 6 pi's cancel, you get 90 times 185, 185 times 90, and then minus, when you plug in 0, you get 0. So 185 times 90, which is about what the heck? Oh, they rounded. Okay. This is about 16,650. And then the measurement here of work would be done in foot-pounds, because everything was measured in pounds and feet. Okay, so that's number 43. Now let's look at number 44. In number 44, they want us to do the exact same problem, except there's a hole in the can of paint, and 9 pounds of paint leaks out of the can during the ascent. So as the guy goes up, right, as he goes up, his as he goes up, the silo, the force changes because his weight's changing, right? So remember, we have 100, how heavy was he? 160-pound man to start. Then you had a 25-pound bucket. And 9 pounds of paint should leak out through the entire trip steadily, so linearly. So when we look at our force is now, we still have 0, 0. Okay, that doesn't change because our force is either straight down or straight up, again, depending on which way you want to look at it. But the force is changing in the z component. It's the original 185, but by the time he gets to the top, he needs to have lost 9 pounds of stuff. And remember that our t is going to vary between 0 and 6 pi. So we need to subtract from this. We need to be at 9 at the top, right? We need a total of 9 to be taken away and nothing to be taken away initially. So it's kind of like what we did earlier, except I'm going to go 9 over 6 pi t. So if t is 0, hold on. hold on a second. This is, T is 0. We need to have, you know what, let me see. There's a couple of ways you can approach this. Yeah, if T is 0, you're at 185, right? T is 0, you're at 185, so that's him starting up. And as he goes up, paint starts flowing out, right? So the weight is changing. And when I get to 6 pi, they'll cancel, and I'll have 185 minus the 9 pounds. So we will have lost all 9 pounds of paint, and it will be linear, and it happens through the whole time interval from 0 to 6 pi. So this, I shouldn't say time interval, this is our angle, but we can look at it as time also. So this is basically the same problem. The only thing is that dot product at the end, remember when you do your dots, that last piece we had for R of t, this was R of t, it was something, 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 and that last one was 90 over 6 pi t. Then when we took the derivative, right, this became just this, and then we dotted. So this will go integral from 0 to 6 pi. We dot these, okay, the zeros kill off, that's why I didn't write them. Then over here, this times this, that's a little bit different, right? So we're gonna have 90, I can take the 90 over 6 pi out. I don't need it. And then I can have the 185 minus 9 over 6 pi. Yes, I could have reduced that t dt. And that's going to be a different answer, right? Because you're going to have to integrate this with respect to t. You get 185 t. Integrate this, t squared 2, so you should have minus 9/12 pi t squared, right? That's the antiderivative of each of those. And then you have a constant out front. You're evaluating from 0 to 6 pi. So when you do that, and I don't think I'm going to do it, you should get 16,245 foot-pounds. So you can see there's quite a bit of difference there because you've lost paint. You didn't have to do as much work. So you have less work done by this guy than the previous problem. But he's lost paint, so he's going to have to go back down and get more.